Now, the second result from yesterday's lecture was that when I have a cascading of two blocks, downsampling and upsampling, where m is not equal to L. So, basically we will make the assumption, make it clear that L is not equal to m, but we have not said anything about common factors. In the general case, the two results are not the same. We derived the expressions. Again, I will not rewrite them, just except to just highlight, saying that in one case the expression has Wmk, in the other case it has Wmkl, and based on the properties of the roots of unity, complex roots of unity, you can show that if L and M are relatively prime, these two are spanning the same set of roots, which means all the distinct roots of unity will be spanned by both of these, and therefore they are equal. Now, if L is not, if L and M are not relatively prime, so basically for example, if they were 3 and 6, or there is some common factors between them, then the upsampling and the downsampling will give you, I mean this operation, they give different, they basically give different results. So, therefore, the results, this result does not hold, that the equivalence is only holds when L and M are relatively prime, otherwise you will get different signals on both sides. Okay. Now, another element that we discussed in the last class was the interconnection of conventional building blocks from DSP, adders, scale factors, multipliers with the multirate blocks, and we said that the multirate blocks are linear. So, therefore, you can do the addition before, after the addition, after the adder block, or before the adder block, does not matter. Similarly, the scaling, similarly the multiplication. These are elements that you can that we have discussed. I would like to build on that and make an observation and some comments on this, because we are starting to now really look at the strength of the signal that we are, of the methods that we are working with. So, basically what I would like you to start thinking about is the following, okay, because it leads us to a very important way of looking at multirate signal processing. So, I have a multiplier, and then I have a downsampler. So, basically one of the essential things that we keep in mind always is that the downsampler throws away samples. So, in this case, this is not a very efficient implementation, because I multiply all the input samples by the scale factor alpha, for example, and then throw away m minus 1 of those. So, this versus the more efficient implementation would be use the properties of linearity and make sure that you do the downsampling followed by the multiplier alpha. This would be the preferred approach. So, basically I will put a star on top of this. That means that is the preferred approach of the two. On the other hand, similar observation regarding the other block, where if I did upsampling by a factor of L followed by a scale factor beta versus the case where, of course, I could move the blocks around. I do the scale factor by beta, upsampling by L, and this would be the sequence of operations. Now, in the first case, there are lots of 0 valued samples. I am multiplying by beta, it is not going to make any difference. I am just going to the multiplication will get done, but a result will be. So, this is a case where this block actually inserts zeros. Insert zeros. So, basically any operation after that will be doing a lot of computations on 0 valued samples. So, this would be the preferred one, where you scale only the input signals and then insert the zeros. So, again this would be the preferred configuration, because it is more efficient. Okay. So, the two, in one case we say that do the decimation as early as possible, because that means down conversion, and do all the processing as much as it after you do the decimation. Same way, upsampling is going to insert zeros. So, do your processing as much as possible before you insert the zeros, and then minimize the processing after we do. So, you can summarize this as in using the following sort of guidelines, rules of thumb. The first one would be minimize wasteful operations. Okay, that is like do not compute and throw away, or do not multiply, or do not do operations on zeros. And this will be one of the ways in which multi-rate signal processing and the tools that we have are going to play an important role. One is first of all minimize, and how would we minimize? Let me call it as 1A and 1B. There is a different strategy when it comes to the downsampler. Basically what we say is minimize computations that are going to be on samples that are going to be thrown away. So, this minimization we would like it to apply to computations to obtain samples that will be thrown away, and keep that to a minimum, because that is going to be that will make the overall system more efficient. Samples that will be thrown away, and this actually turns out to be one of the foundations on which we do polyphase decomposition and the noble identities, which we will be looking at in today's lecture, that will be thrown away. So, that is for a downsampler, will be thrown away, and that is primarily linked to the downsampling operation. Okay. Then 1B will be avoid computations, minimize computations on zero valued samples. Computations on zero valued samples, and this basically is another way of saying what I had already mentioned. For a downsampler, try to do the downsampling as early as possible, and therefore and then the processing. For the upsampler, do the processing first and then the upsampling process. So, that way you will satisfy 1A and 1B, and that will give us a overall efficient implementations. Okay, now having understood this, and very happy that yes, multi-rate gives us some significant tools to work with, we go back and say what do I do when do we have computations that go along with the upsampling and the downsampling? Most of it is when we do sampling rate conversion, it is the filtering that goes along with it. So, let us look at filtering with upsampling and downsampling, okay, with up or downsampling. Okay. So, the first case that we have looked at is when you did upsampling, you said we made the observation that we would have to follow it up with an interpolation filter. Now, why do I do an interpolation filter? To remove images. When does the images come? Because I insert zeros. Now, does it make sense to say do the filtering before the zero insertion? No. So, you kind of say, well, I am stuck. Though I realize that I should not be doing a lot of operations on zero valued samples, I may not have an option, because this is a case where, okay, so this is one that's sort of is going to, I will put a question mark saying, okay, I am not going to be able to achieve or utilize some of the observations in the previous one. The second case that we looked at was when I want to do downsampling. In that case, we said, okay, precede it with an anti-aliasing filter, okay, and then followed by the downsampling. Okay. So, the most common or the simplest of operations that you would combine with upsampler and downsampler are the corresponding filters. Of course, there is a lot more that we will do and we will study, but at the foundational level, these are the two operations. Now, this one also is conflicting with the requirement, because what does it say? If you are going to do downsampling, do not do all the operations and throw away samples. But the problem is, if you ask me, if you do the downsampling without doing the filtering, then what will happen? Aliasing will come in, and then I will be in bigger trouble. So, again this says, well, there is a big question mark saying, okay, what do I do? There is probably nothing, because in both cases the filtering needs to happen where it is happening. In one case it is happening after the insertion of zeros, in the other case is before you throw away samples. So, really how do we take advantage of that? So, we see that there is possibly a conflict with the observations that are above. So, is there a conflict? The answer is yes. Okay, yes, there is a conflict, there is nothing I can do, we said. So, then how do we address this? How do we address it? and this is where the sort of the beauty of multi-rate signal processing comes in. We will look at how do you address this fundamental issue. Okay, that is the question that we answer in today's lecture. Okay, so this is the part. So how do you do the operation so that those are happening in the most efficient and efficient possible manner. Okay, so let's quickly dive in and build the blocks that we need and develop that. So first of the observations that we will want to come up with. Okay, this is a observation number 1. I want to look at downsampling followed by filtering. Okay, now let us assume that this is a particular scenario where I am not so much worried about the anti-aliasing part. Let us say there is some processing that is happening on the downsampled signal. So this is a very important step, and you will see in a moment why it is so. So if my input is x of n and my output is y1 of n and intermediate signal is x1 of n. Now can you please help me write the expression for y1 in terms of x of n? It is straightforward. Let us first write down x1 of z, that is a downsample signal, 1 over m summation k equal to 0 through m minus 1 x of z power 1 over m w m k, okay, that we are comfortable with. Now why is the x1 of n filtered through h of z, and so we can write down the output expression y1 of z is equal to h of z times x1 of z. This can be written as h of z and within the bracket 1 over m summation k equal to 0 to m minus 1 x of z power 1 over m w m k. Okay. I do not have a direct input output relationship because this is not an LTI system. Right. I have x of z and I have shifted versions, and of course there is frequency scaling and all of that is present in the picture, but nevertheless this equation is correct between y1 of z equal to h of z times this expression. There is nothing wrong in this equation, this is correct. Now I would like you to apply or focus onto the following structure, another structure where I have the input x of n, same input, but this time I am going to modify my filter h of z power m. If I give you a h of z which is a low pass filter, what will h of z power m be? It will be a multiple pass bands. It is a band pass filter. It passes low frequencies, but it also passes several bands in between. So, and does it also pass high frequencies? It does, right. Well, we do not know, depends on where these images will come. Certain values of m you will get the high frequencies also, but interesting, you think about what h of z power m looks like. Okay, so h of z power m is what we have, followed by a downsampler, and this output I will label as y2 of n with the intermediate signal being x2 of n. Okay, please write down the output for this. The first step says I have x2 of z, that is h of z power m times x of z. y2 of z is a downsampler 1 over m summation k equal to 0 to m minus 1 x2 of z power 1 over m w m k. Right. Now please substitute for x2 of z from the earlier equation, and please do verify that the result that we get is actually h of z times 1 over m summation k equal to 0 to m minus 1 x of z power 1 by m w m k, which means that we have y2 of z is actually equal to y1 of z, which means y2 of n is the same as y1 of n, which basically means that these two blocks are one and the same. So, this block is the same as this block. These two are the same, the green boxes are the same. So, I can equate, I can actually draw downsampling by a factor of h. So, let me just maybe do that. Downsampling by a factor of m followed by h of z is identically equal to filtering by h of z power m followed by downsampling by a factor of m. These two are identical. Okay. Now, very easy to see the principles that we have said in the last lecture, earlier slide, which says that it is always advantageous to do the downsampling first followed by any operation. So, which says that this of these two, this will be the preferred structure. Okay. Now, go back and look at our whenever we want to do anti-aliasing filtering, it comes out into this form, right, it comes out into this form. You have to filter first and then downsample. So, if my processing before downsampling can be written as a filter which is h of z power m, something which has the same exponent power as the downsampling factor, then I have a very efficient implementation. Now, go back and look at the counterpart example. So, I have input x of n, I want to pass it through a filter h of z followed by a upsampler by a factor of L. Let me call the intermediate signal as x3 of n and the output as y3 of n. Please give me the expression for y3 of z. This is fairly straightforward. x3 of z will be h of z times x of z, that is the filtering operation. y3 of z is x3 of z raised to the power L, wherever there is z I have to substitute, replace it with z power L. If I use it in the previous equation, this becomes h of z power L x of z power L. Okay. Maybe it is already obvious from the expression, but we will just write it for completeness. It says that the structure, if I do the following, upsample by L and then multiply or do the processing with h of z power L, what will it be? This is x of n, x4 of n, y4 of n, x4 of z will be x of z power L, output y4 of z will be, so just write down the final answer, y4 of z is nothing but x of z power L h of z power L. So, here again we have shown two structures that are equivalent. Let us capture that information in our result, which says that if I have a filter h of L, h of z followed by a upsampler, this is identically equal to an operation where I have upsampling by a factor of L followed by h of z power L. Okay. These are exactly equivalent, and of course, going back and looking at our basic premise, upsampling introduces a lot of zero valued samples, better to do the processing before you do the upsampling. So, which says that this is the better or the preferred of these two structures, this would be the preferred one. When we want to do interpolation, I have to follow it by the interpolation filter. Unfortunately, this is not an interpolation filter, this is h of z power L, which is not a low pass filter. So, maybe we can just make a mention of it, which says h of z power m or h of z power L, these cannot be low pass filters, so you cannot interpret either of them as an anti-aliasing filter or as an interpolation filter. Nevertheless, if you can whatever processing that comes in a after upsampling, if it can be clubbed in the form of h of z power L, you have a very efficient implementation which is in this form. So, the question was, can a low pass filter be written in this form, and I am glad you asked, because maybe we will answer that question. That was supposed to be after the next section, but that does not matter, we will answer it. It is a very important question. Let us answer that question, and you will see that the beauty of multirate signal processing actually emerging from this very simple slide. Okay. So, if I were to look at a low pass filter with impulse response h of n, okay, it is a low pass filter. Some just for argument's sake, let's assume that it is an FIR low pass filter, finite impulse response low pass filter. H of z will be summation over n h of n z power minus n. So, if you were to write this down, what will it come out to be? Let us assume that it is a causal filter. It will be h naught plus h1 z inverse, h2 z minus 2. I will write up to h6 just for just to illustrate. h3 z power minus 3 plus h4 z power minus 4, h5 z power minus 5, h6 z power minus 6. Okay. Now, if I were to group these even terms of the impulse response, I would get h naught plus h2 z power minus 2 plus h4 z power minus 4 plus h6 z power minus 6 plus z inverse, or let me just write it like this, h1 z inverse, h3 z minus 3 plus h5 z minus 5, which can be rewritten as z inverse times h1 plus h3 z minus 2 plus h5 z minus 4, right. So, I can write this as h naught of z squared, some polynomial with argument being z squared, not z anymore, it is z squared, because all of them are even powers, plus z inverse h1 z squared, correct. So, this is I am calling this as my polynomial h naught, and this not without the z inverse as my polynomial h1. Now, here is the beauty of what we have been talking about so far. I want to do down conversion by a downsampling by a factor of 2, which means I must precede it with an anti-aliasing filter. So, I have h of z, which is going to be followed by a downsampling by a factor of 2. This structure is not efficient because I am doing the processing and then throwing away samples. However, if I do this sort of splitting, then I can say that this is identically equal to the same filter, but now written as h naught of z squared plus z inverse h1 of z squared, followed by a downsampling by a factor of 2. Okay. Please draw for me a structure that implements this. I separate out the blocks, h naught of z squared, then another block which says z inverse h1 of z squared, parallel convert, and then you have to add the outputs together. So, the input x of n gets filtered by h naught of z squared, that gives you one output, and then the same input is filtered by z inverse h1 of z squared. These are linear blocks. So, therefore, I can write it as a single block, or I can separate it out, basically the way you would create filter structures. These are identical. So, basically this is what we are doing, and now I have to follow it up with a downsampling by a factor of 2. Am I right? That is the process. So, I do the filtering followed by the downsampling. Everyone with me so far? H of Z is the anti-aliasing filter. I want to do downsampling by a factor of 2. As the question was raised, can I group terms to make them not polynomials of Z, but polynomials of a higher power of Z, which is exactly what we have done. Now, invoke the property of linearity, which says that I can take the downsampler inside. Okay. So, which means that I can take the downsampler inside. So, I can insert a downsampler on the upper branch, I can insert a downsampler on the lower branch. What does in fact these results are actually what we refer to as the noble identities. I forgot to mention that. These are the noble identities. The noble identities basically tell us which is the more efficient structure from a multirate viewpoint. So, now if I were to apply the noble identities identity for this combination, it says I can interchange the order in which they are done. The better order will be downsample by a factor of 2 followed by not H naught of Z square, it will be H naught of Z. Similarly, I cannot operate on Z inverse H1 of Z square, because that is not a polynomial with power 2. So, I am going to separate it out as a delay element followed by H1 of Z squared by downsampling. Again apply the noble identity. Noble identity says you can do downsampling first followed by H1 of Z. And then of course, you have to add the two signals up together. Now, tell me what is this? What is this? It is a demultiplexer. Which way is the commutator switching? So, counterclockwise, but in a 2 channel case it does not matter whether it goes counterclockwise or counterclockwise, but the important thing is so what is this data going in the upper branch? X0, X2, X4 dot dot dot, lower branch X1, X3, X5 dot dot dot. Okay. Each of these is getting processed by a filter of half the length and then added to produce the output. Nothing is wasted, no computation is wasted, because you made it as efficient as you can, because in the original case what were you doing? You took x of n, you multiplied it with h naught, you filtered it with h1, then you threw away half the samples and then finally obtained the output. Now, this you can see is the power of multirate signal processing. So, whether it is upsampling or downsampling with the appropriate filtering, this is what we refer to as polyphase decomposition. Polyphase decomposition probably was the discovery that made multirate signal processing, sort of opened up the world of multirate signal processing. So, what you will now find is that any filtering operation, you can now apply the noble identities to make it very, very efficient, because just as you did the downsampling by a factor of 2, what I would encourage you to think about is the upsampling by, let us say, by a factor of 3. Upsampling by a factor of 3, which you would then have to follow up with an interpolation filter H of Z, which I would like you to now think of it in terms of H naught of Z cubed plus Z inverse H1 of Z cubed plus Z minus 2 of H2 of Z cubed. Okay, instead of one polynomial, I wrote it as 3 polynomials, each of which are powers of 3. But with the Z minus 1 and the Z minus 2, you get all the powers of Z. So, using this equivalent representation, can you draw for me the most efficient interpolation operation? Derive the most efficient interpolation, and you will find that you are not doing any operation on any non-zero samples. It is the beauty of this, is most efficient structure for interpolation, for upsampling by 3 plus interpolation filtering. Okay. So, what you will find is that we have introduced 2 very, very powerful concepts. One is the noble identities. Initially, first glance of the noble identity says, well, what use is this, because it is not fitting in with my framework. The next comes polyphase decomposition, which says, hey, you can always split your filter into sub filters, and then all of a sudden the opportunities to use the decomposition. And you will find that in this case, just like you got the demultiplexer in the case of the anti-aliasing filtering, what you will find in this case will be the multiplexing operation. Please try it out. We will start from here and build on it in the next lecture. We will see you tomorrow. Thank you.